I was trying to make a coil, a radio coil, to receive the time signal in Germany. It works on 7.5 kilocycles, so that's a very low frequency. Anyway, you can buy these time modules on Ali. They are very cheap, say 4 euros or so, etc, etc. But my idea was, well, let me try to make a coil that I can tune to that 77 kilocycle frequency. And this is a first experiment. I'm absolutely not sure that this will succeed, but anyway, 300 windings here on that plastic tube. Here is the diameter. I don't give now the exact measures of the coil anyway, because it's still experimental, etc, etc. You can test such a coil by connecting it to a test oscillator, and that's here. I will give the link in the description. I've used it many times. There are also other videos on my YouTube channel where I've used this test oscillator. And here are some conclusions. We know that this is a coil, but in, say, radio terms, this is a so-called tank circuit consisting of a coil and a parallel capacitor, and here in between all the windings there's also capacitance. That's important to tell. So when you don't use this coil with a separate tuning capacitor here, this can also be a variable capacitor, that coil will oscillate on a certain frequency, and you can use that test oscillator here, and I'm going to do that now. And this test oscillator has some settings, and via the settings you can see how fierce the oscillation is. So you can turn it here. So, and this is what I wanted to tell. Here is the first setting of the oscillator. There is a capacitive voltage divider in this field effect transistor oscillator, and here you see the different capacitors that are used. In position 1, this is the, say, the capacitive voltage divider, position 2, etc, etc, but the idea is that it goes here to higher frequencies. So you can search on which frequency band, more or less, here are the frequency bands, where this oscillation is at its maximum, and in that case the quality factor of the coil is at its highest. So there's a relation between how the coil is made, etc, etc. So I want to demonstrate that now. Now we go, say, from the lowest band in the oscillator to the highest band. This is position 1, it doesn't oscillate. Position 2, small oscillation. Position 3, more fierce oscillation. Position 4, fierce oscillation. Fierce oscillation. Position 5, fierce, etc. So it means that this coil in this situation, without a tuning capacitor, works at its best on these frequencies. And you take the counter in that case, and you can see it is 670 kilocycles. Switch it back here. 3 to 5 kilocycles. Here it performs not so good on 174 kilocycles, and here it doesn't. Well, this is 90 kilocycles. I have to put up the amplification of the scope. But anyway, say the quality factor of the whole situation is on this frequency not very high. And that means that when I want to use this coil in a radio application, it will receive much better frequencies in these higher ranges. So in these frequency ranges, here is the ideal frequency. 3 to 5 kilocycles. Anyway, but of course, let's add a capacitor. This is a capacitor of 1.5 nanofarad, that is 1500 picofarad. And of course we know that when we bridge a coil with a capacitor, the frequency in this case goes down. And there's also again, now it is connected here, there's also again that relation to the highest quality, the highest Q, so where it oscillates at its best. With that parallel capacitor, we have here that tank circuit here. We have this situation that with a say we can get the bandwidth very small, so a high quality factor, when we use much L, that is inductance, and a low capacitor parallel to that same tank circuit. And when we have here a high capacitor and less inductance, the frequency gets more broad. And I want to demonstrate that here again by these settings. Because we have now connected a parallel capacitor, we are on 134 kilohertz. So let's see where the Q is at its best with that parallel capacitor. Of course, we get now to a lower frequency band. So, well, no good results. It means, in general, that this is, say, the ideal frequency for this coil. This coil with this capacitor, 1500 picofarad, and it is 134 kilohertz. But when I want to go to lower frequencies and have again a high quality factor, there are a lot of possibilities in all the early time detecting circuits on 77.5 kilocycles. They use a Ferrite rod with a Litze coil on it. Litze is a typical special piece of copper wire. It's entwined. Say we have 30 windings or so entwined. And that means that the quality factor of such a coil gets very, very high. I don't want to use it, Litze wire, because I don't have it. And it is very more or less difficult as a radio amateur to solder it. You have to solder, say, 30 wires of that tiny Litze wire at once. And that's difficult. Anyway, so for my simplicity, and perhaps everyone looking at my YouTube channel, I use this type of copper wire and try to get the same result. That is a difficult thing, by the way. So that was more or less all to tell. Thanks for watching. Hope it was not too long. The best idea in this case, to say get an air coil on that low frequency, 77 kilohertz, must be that we have more windings here, so more than 300 windings, and use it with a small capacitor to get the highest Q, the highest peak resonance when receiving that radio station. Important to tell, this is a Ferrite rod. You can stick it inside that coil, and I can surely demonstrate. I stick it in now, and you can surely see that the frequency changes. You can see it here. It gets lower. So here you can read it. The Ferrite core is out. Put it in. counter cannot take it. 116 kilohertz when the Ferrite rod is sticked in, and 134 when that Ferrite rod is out. And the reason is that the inductance of the coil changes very substantially when you put something of this Ferrite rod in. When you put in a piece of steel or so, the oscillation will stop. That means that steel has no good properties to get such a coil into a lower frequency or with a better Q, better quality factor. Thanks for watching. I'm absolutely not sure that this project can work. I did a few simple tests, made this radio for instance, with no success, but anyway, perhaps also the way to make that circuit, whether it succeeds or not, is perhaps interesting when you are interested in serious radio experiments. Thanks for watching and a happy Easter.